So populations, Unit 3 is on populations. We start out looking at the different ways in which different organisms will basically populate, or they'll reproduce in order to keep their species going from year after year. And there's two main strategies, the K and the R strategist. Your K strategist is what we are, and I would say pretty much all mammals are. They will tend to have a long lifespan. They'll produce few offspring, relatively speaking, over their lifespan. And they take care of their young. Like I said, all mammals. Mammals specifically have the organs that are made to do that. That's what makes mammals mammals, by the way, is the presence of mammary glands. And they will tend to follow what's known as a S-shaped growth curve, or a logistic growth curve. And we'll go into details about that in a minute. It's important you know the parts of that. And then their survivorship curve is one where they tend to, also we'll look at survivorship curves, but they tend to go at a high survivorship when they're young because their parents take care of them and protect them, and then they start to fall off and die off, of course, when they get older. So it tends to look like that. They are limited primarily by density-dependent limiting factors. That means as it gets too overcrowded, things like starvation, disease, and those kind of things will tend to cause their population numbers to drop rapidly. It's an increase in the death rate when that happens, and then when they start to recover somewhat, then their number will jump back up, and it'll kind of go fluctuate up and down around what's known as a carrying capacity. So the how much that particular ecosystem can support of that species is what we call the carrying capacity. So K strategists tend to do that. And then we have R strategists. These are your microorganisms and insects and things like that live a very short lifespan. They tend to produce large numbers of offspring, but they don't take care of them. They're out on their own, hatched and going right from the start, and they tend to lose a lot. They have what we call a low survivorship curve when they're younger, but so they produce so many. They offset that by producing large numbers of it. They often act in a seasonal kind of resources available type of reproductive strategy, so that when things are good, they'll make babies, etc., and they'll have eggs or some other way, spores that will allow them to their offspring, which is their eggs and their spores and stuff, to survive into the next season, so that their young will then hatch and be out in the environment, and they'll do the same thing. And so they have a lot of times they have these short life cycles, like insects, and fish are the same kind of way, many species of fish, and that's how their numbers keep going from year after year. So they tend to have a J-shaped growth curve where their population numbers grow way up, and then they drop way off, and they go back up again. They tend to, as I mentioned, will have a low survivorship when they're young, but if they make it, they tend to live a long time. And I use the example for this one of sea turtles, because most people are familiar with the sea turtles marching off. They have 80, 90 eggs, which is a lot for an animal that size. Keep in mind, it's not the thousands you see with bugs and microorganisms, but it's a lot. And then very few of them actually make it to the ocean, but once they do make it to the ocean, they survive. They would tend to live a long time. Another example from the plant kingdom is like oak trees. Trees put out thousands of acorns. Very few of them will actually grow into a mature oak tree, but once they grow into that tree, it's there and tends to survive for a long period of time after that. So they are oftentimes more limited by density-independent limiting factors, which are things that are going to change or things that happen regardless of the population. So it doesn't matter how many mosquitoes there are out there, winter's still going to come, summer's still going to come, the seasonal cycles are going to go through, or if they have changes like a lot of species of plants and stuff where storms like hurricanes will clear them out. That happens regardless of how much is there, what the population density is. So they tend to be killed off by what we call density-independent changes like that. Okay. All right. So we got a couple of curves you need to make sure you're familiar with. The parts of this curve here. So the curve we're really talking about here is this part here, the purple line. Okay. And there are certain parts of this that you should know. First of all, you have a lag phase down here where they're just trying to kind of get established. Then they go through what we know is an exponential growth phase, and this didn't really draw it well, but an exponential growth phase technically, or an exponential growth mathematically, is actually a curve. And it curves up because of the fact that it is getting faster, and the rate at which it's getting faster is increasing as well. It's like an accelerating car. You'll learn in physics if you haven't done this already, that speed is a linear relationship, but acceleration is a exponential curve because it gets greater by a greater factor every time it goes up. So in case of organisms, it's because you have offspring, and then assuming you have at least 2 or more offspring, those offspring will then also have their offspring, and so then it keeps branching out and growing and growing and growing like that. So we call it an exponential growth phase. Eventually, they hit the point where they get overcrowded. This was described before. And so their numbers drop off, and then they pick up again, and they'll kind of fluctuate around here.
This is the R strategist, right?
This is a K strategist. Big K. Think Big K, if you can remember, they used to call Big K.
You said the R is the one that goes up and down, up and down, up and down.
So they go up almost up and down right here. Okay. So as you can see here, this one's just fluctuating around a value right here. Look at the graph here. So it fluctuates, it goes up, and then it recovers a little bit, goes up, and establishes a constant population number right up around this carrying capacity right here. Okay, so ignore the fact that it's important that you know that it does fluctuate around. It doesn't just hit a number and stay the same all the time, but it hits an area where it tends to stay there around that particular area. That's what we call the logistic growth curve. Now the R strategist, on the other hand, which is right here. That is going to be where the mosquitoes. It gets hot and rainy. Their eggs hatch. They get out in the air, and they find each other, and they mate, and then they lay their eggs again. And then when it gets cold again, boom, the population drops way down. Right, Mr. Reeland? You see the difference there? And then when it gets warm again, boom, population numbers go up. But just think of it yourself. Think of these bug populations in particular. That's something you can see in everything. Though sometimes a year they're all over the place, and then other times a year there's nothing there. Okay. Whereas squirrels, though you don't visualize this unless you're outside counting squirrels all the time, but if you watch them, you probably could, if you surveyed them, there's always a certain amount around, but you would probably see their population numbers fluctuate around that.
But not as dramatic as
Correct, not as dramatic, and once it hits this area, it tends to stay here. Our strategists are going to always be going up and down, up and down. So that's a big difference there. And I can see what you mean by this one is up and down also, but it's much more controlled up and down. And the main thing it stays right around this particular number here. Any questions? K versus R strategists and the growth curves that they have there. Exponential growth phase, and make sure you understand that's what that means there, what the term exponential growth means, that it increases, and it increases by more each time. We can represent it with an exponent, that kind of thing. All right. And then, there's your survivorship curves. So understand that K strategists tend to have this kind of survivorship curve here. Now, that doesn't mean that, as you can see here, there's one in the middle. That doesn't mean these are K or R strategists. Typically, birds are classified as K strategists. They have a few eggs usually, or I don't know the maximum amount they typically will have, and they can take care of their young. So they're definitely in the R strategist category. But for some reason, their survivorship curve is different from both of them. It's like right in the middle. There's an equal chance of dying at any point in time. On the other hand, with the K strategists, like I said, they will survive their youth, they get raised, their survivorship stays up here, and then eventually, of course, as they get older, people are going to start dying off. Down here, your R strategists, lots of offspring, only a few survive, but they survive to carry on for quite some time, typically. For that. Okay? Questions about that? No, that's population ecology. The other part of Unit 3
what's in the middle?
Is, pardon me?
That's
the one there. That's just one that has an equal chance. See, the survivorship means what is the likelihood of it surviving. So with an R strategist that puts out lots of seeds or lots of little baby turtles, etc., not a very high chance of survival. A lot of them die young. And then they go on to, live to an old age, those few that do. K strategists, a lot of them do survive, and then they die off when they get older as well. Okay?
The
Anybody
eagle
else?
be in K then?
Pardon me?
Would the eagle be a K?
Eagles are, that's the one that you can't really break it down. They do have a middle category. Eagles in general are K, and birds in general are K strategists.
Yeah.
Because of the
They
fact
feed their young.
they take care of their young. They don't tend to have that many of them, really. And those are the two main things that make them K strategists. They live a fairly long time. You get a parrot, a lot of people, their parrots out they live like 80 years or so. Parrots do. Parrots. Alrighty, so that moves us into human populations. Okay? And so what we see is a progression. This is totally sociology now. We didn't really completely transitioned out of biology. And we're talking about human populations, and of course that is important because we're going to look at it this way. Where a society is in the what we call the demographic transitions represented here is going to impact both its population numbers, and each person has impact on the environment, and their technological development, and that also has impact on the environment. Of course, that's what this course is about, is impact, the human impact on the environment. So we see 4 different phases here. At the beginning phase, this is a almost completely agricultural, pre-industrial society, we call it. And at that phase, they have high birth rates and high death rates. The birth rates is a fertility rate. The women tend to have more children. And then the death rate is high because of a lack of medicine and food and sanitation. Okay? And then you hit the phase that actually, so these are pretty rare. There's pockets of these in many countries, but as far as a whole country being this way or major societies being this way, this is pretty rare at this point. Where most of the world is that at the point where they have been introduced to the food, medicine, and sanitation, and so because of that, their death rate right here, that drops down. So a lot more people survive, a lot more babies survive, etc. But the birth rate is, that's something actually that the family decides upon. Really, it's the man that typically decides upon it. But it's a societal tradition kind of thing. It's not driven by resources as much as it's just driven by the way people react with each other as a culture. What's expected, particularly of women in that culture. And so birth rates tend to remain high for a while in these societies while the death rate drops off. That means, of course, the population growth is the birth rate minus the death rate, so keep that in mind. You may hear that again. Birth rate minus the death rate. So this big gap here represents a rapid increase in population. And so much of the world is at that point right now. And you can see much of Africa, India, etc. is there. And then something different happens here when we get towards the industrial phase. And this point, really, the crossover point where the birth rate starts to drop is where women start to have more control in the society. They're able to make more decisions as to how many children they want to have. And it also becomes an advantage for your average family to have both spouses working. It becomes a financial advantage to do that. And therefore, they go to school, they start their job before they start having children. Birth control, of course, is another big factor. There's more availability of that will cause this to come down. And so the birth rate now drops during the industrial phase of the demographic transition. Okay? And the United States and many other industrialized countries are in this phase right now. And because of that, as that birth rate gets near the death rate minus death rate is population growth. The rate of population growth here is the slope of the line, not how high it is, that's just overall population, but how much of a slope it's growing at, that slows down. Okay, until it approaches 0 as the birth rate approaches the death rate. Then, after that, you can get into a post-industrial society setting where, according to this, Germany, but also Japan, they've got Japan over here, a lot put it in post-industrial. but where your death rate is actually greater than your birth rate, and the population numbers actually start to shrink. So that's something that you can see, and it actually becomes a problem in these societies with their economy and everything. The fertility rate, so make sure you understand that population growth, this is total population, is how many people total. Population growth rate is how much does your population increase or decrease every year, right? That's going to be birth rate minus death rate. Fertility rate, listen up. Fertility rate is an important thing to understand. That's the average number of children that a woman has in that society. So what we see here is it's high here and high here, which is what leads to, but it's not the same as, but it's what leads to the high birth rate here, is the average fertility rate being high. And then as we move along here, it starts to decrease. And make sure you understand the, I put it in the other one here. The concept of replacement fertility. This would be a good time to look back at that. That's it, there it is. All right, so this table also breaks it down. If you look back at your notes, please still have your notes on this. But fertility rate to replacement fertility. So the idea of replacement fertility is the fact that you have two parents, and therefore, if you want to keep your population flat and at zero, then those parents need to have two children that survive and go on and have two children of their own, on average, right? And so that's a replacement fertility, but you have to bump that up a little bit because not all children will survive to have children of their own. So that all depends on perfect scenario of everyone growing up and having their own children. So if they don't, then you have to give it actually a higher number. You're going to have more children to keep the population at zero, basically, to replace yourselves, replace your parents, and that kind of thing. So you have to have more than two. So in the societies where you are less likely to survive to adulthood, that makes it a higher replacement fertility rate. And so that's part of the reason why in your pre-industrial society the fertility rate is very high, because they have so many children die and people die young and that kind of thing. So replacement fertility is going to be up there right around the actual fertility rate. So that tends to be around 3-ish. Okay. Then when you hit the transitional, that's the point at which your fertility rate. Remember the societal norms and everything don't change right away. So women still have a high replacement fertility rate, but it doesn't need to be as high anymore because you don't have as much. You have more children surviving to adulthood. So it's that point where our replacement fertility. Or your fertility rate in which women are surviving children, is greater than your replacement fertility. Basically, you have more children than you need to. That's why population growth is rapid. When you get here where the fertility rate comes down, and for the replacement fertility, you get back to your FR equals RF value again. And then if you hit a post-industrial, then your fertility rate is actually less than replacement fertility, and that's why you end up with a negative population growth. You're not having enough children to replace the parents, and so that by necessity, eventually the population is going to start to shrink. Now, keep in mind that necessity part. There's something called population momentum, which means that the population numbers, when your fertility rate drops, population numbers will actually stay high for a while. And that's because you're basically waiting for the offspring to die off before you. That's before you will actually start having negative population growth, because the old folks stay around. That's the other thing about it as well. You get more of that population momentum because as we get in here, of course, healthcare is better. These highly industrialized societies tend to have higher life expectancies, and so that means that the population will stay up for a while longer.
So there's like no growth in industrial society.
Slow to zero. Slow to zero, yeah. Like the United States, for example, has
Slow to zero.
it has a slow population growth rate, but that is mainly because of immigrants and the fertility rate that you tend to see with those immigrant populations is higher.
Downward, right? Decreasing?
Yes. Yeah. And Germany as well. So So here we see, these are age structure diagrams. What you see in these transitional societies with the really high population growth rates, a lot of youngsters, okay? A lot of, in the past, they didn't survive. So now in the past 40, 50 years or so, or, well actually in the past 20 years or so, they still having these high fertility rates, lots of children around, and therefore they have a very wide base. They still kind of have less life expectancy, so this tends to narrow still at the top. The key here as to why they're going to have such a fast population growth is that you can break this up into pre-reproductive and then reproductive, basically like that. 15 to 45 typically is what we call the reproductive years. And so if you've got a lot here that are going into this age group over the next 10 years, which is how often they do population studies, that society is going to grow the fastest. This is going to have about an equal rate of people going into the reproductive years as well as people coming out. So that's a big difference there. So you're going to have zero to slow growth there. And this area, as you can see here, we call it the coffin shape here. Oops, that's terrible. With this society, the coffin shape, basically, because it's a dying society, you've got more here going into the post-reproductive age, and of course you've got a big chunk here that's simply dying, and therefore that will tend to have a shrinking population.
Pyramid shape. Oh wait, no,
A
diamond.
coffin.
Coffin.
Coffin, you know what a coffin is, right? You know what a coffin looks like? Yeah, so that'll make you understand it's older, it tends to be an older society, and it tends to be dying, so.
Oh, I get it.
Yeah.
Coffin.
This is more like a pyramid, so if you can somehow associate pyramids with,
Growth.
yeah, that type of society, then you're good to go. Alright, so that was Unit 3.